Einstein's biggest mistake came back and changed cosmology forever. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. For discussion, write down your views in comments. More than a century ago, Albert Einstein made a change to his theory of gravity that he would later famously regret. He introduced something called the cosmological constant, a term designed to keep the universe from changing. Einstein believed the cosmos was essentially static, but his own equations were telling him something very different. The universe should either expand or contract. So he added a new term that could counteract gravity and hold everything in balance. Years later, after observations revealed that the universe really is expanding, Einstein abandoned the idea. The cosmological constant became associated with what he reportedly considered his greatest blunder. But decades after Einstein discarded it, this supposedly unnecessary term made one of the most dramatic comebacks in the history of cosmology, and it eventually became a central part of our best model of the universe. Today, however, there is an intriguing problem. That model works extraordinarily well, yet scientists increasingly recognize that it may not represent the final answer. To understand why Einstein introduced the cosmological constant in the first place, we have to go back to 1917. Only a few years after he developed general relativity. Einstein had realized that gravity was not simply a force pulling objects together. Instead, matter and energy influence the geometry of space-time itself. Naturally, the next question was enormous. What does this theory predict for the entire universe? On cosmic scales, gravity dominates because electromagnetic forces tend to cancel out over enormous collections of matter, while the strong and weak nuclear forces operate only across extremely short distances. When Einstein applied his equations to the cosmos, he discovered something unexpected. A universe filled with matter should not simply remain frozen in place. According to general relativity, the universe should evolve. It could expand or it could contract, but the prevailing scientific picture at the time assumed that the universe was essentially static and unchanging. Einstein therefore faced a problem. His equations were predicting a dynamic universe, while observations and accepted thinking suggested a static one. Einstein's solution was to modify his equations by introducing the cosmological constant, represented by the Greek letter lambda. In simplified terms, lambda acts as an additional property of space-time itself. Depending on its value, it can produce an effect that counteracts the attractive influence of matter. Einstein selected a value that would balance cosmic gravity and keep the universe stable. But that carefully balanced picture soon began to collapse. Within a few years, observations associated with Edwin Hubble showed that distant galaxies were moving away from us in a way that revealed the expansion of the universe. At the same time, theoretical work by scientists, including Alexander Friedmann, showed that Einstein's equations naturally allowed an expanding cosmos. The idea of a dynamic universe became increasingly difficult to ignore, and Einstein eventually abandoned the cosmological constant. Then, more than 7 decades later, something extraordinary happened. In 1998, astronomers studying distant exploding stars were trying to determine how the expansion of the universe had changed over cosmic history. They already knew the universe was expanding, but gravity should have been slowing that expansion down. Matter attracts matter, so the expectation was that the expansion would gradually decelerate. By measuring distant cosmic objects, researchers hoped to determine exactly how much the universe had slowed, and perhaps resolve disagreements about how much matter the cosmos contained. Instead, the observations produced a result nobody expected. The expansion wasn't slowing down. It was accelerating. Something appeared to be causing the expansion of the universe to speed up over time. The simplest explanation was remarkably familiar: Einstein's abandoned cosmological constant. If empty space itself possesses an energy associated with lambda, that energy could produce a repulsive effect on cosmic scales and drive accelerated expansion. the supposedly discarded idea suddenly returned to the center of cosmology. Scientists began referring to the mysterious phenomenon behind the acceleration as dark energy, and the cosmological constant became the simplest mathematical description of it. Einstein's old idea had effectively been resurrected, not because scientists wanted to revive his mistake, but because observations appeared to demand something remarkably similar. This discovery helped establish the modern Lambda-CDM model, which has become the leading framework for describing the evolution of the universe. The lambda represents the cosmological constant or dark energy, while CDM stands for cold dark matter. Together with general relativity and a relatively small number of parameters, this model can describe an astonishing amount of cosmic history. It can account for the expansion of the universe, the cosmic microwave background, baryon acoustic oscillations, the formation and growth of galaxies, and the enormous large-scale structures that stretch across billions of light years. Few scientific models have ever been tested against such a wide range of observations. In that sense, Lambda-CDM has been remarkably successful. But there is a twist. A model can be extraordinarily successful and still not be the final truth. The biggest mystery is perhaps the simplest looking part of the model, lambda itself. Dark energy appears to dominate the energy budget of the modern universe, yet scientists still don't know what it actually is. Is it truly a constant property of empty space, exactly as Einstein's cosmological constant assumes? Or could whatever is driving cosmic acceleration change with time? If it changes, then Lambda-CDM may only be an approximation of a deeper theory, and this is where cosmology becomes especially fascinating. Einstein originally introduced the cosmological constant because he wanted the universe to remain static. He later abandoned it after the discovery that the universe was expanding. Decades later, observations revealed that the expansion wasn't merely continuing, it was accelerating, bringing lambda back from the grave. Today, the same concept sits at the heart of our most successful cosmological model, while scientists continue testing whether it truly describes the universe or whether something more complicated is hiding underneath. So Einstein's greatest blunder may have been anything but a simple mistake. It became a concept that helped transform our understanding of cosmic evolution, and it may still hold the key to one of the biggest unanswered questions in modern physics. The universe is expanding, that expansion is accelerating, and we have a remarkably successful model explaining why, but we still don't fully understand the mysterious force, energy, or property of space-time responsible for it. Perhaps the strangest part of the story is that the clue may have been sitting inside Einstein's equations for more than a century. The question now is whether lambda will remain the answer, or whether the next revolution in cosmology will finally show us that Einstein's mistake was only pointing towards something even deeper.